Okay, this is the final unit of modern physics, and we're going to clean up a little bit here with the models of the atom and talk about a guy named Davison and Germer. And what they did is, if you remember the double slit experiment, where we passed waves through two openings, they diffracted, and you remember from the waves unit that that is the bending of waves, and then they interfered and they left a pattern of light, dark, dark, and that was proof that light behaved as a wave. But what Davison and Germer did was they passed electrons through the double slit, and they found that they left a similar pattern. And what that did was basically show that electrons are waves. Now, we know that they also have particle attributes, so just like light is both a wave and a particle, they discovered that electrons are waves and particles. So it turns out that all matter, protons, neutrons, all the different particles, have both wave and particle nature to them. So then along came this guy named DeBroglie, and what he did was he said that the reason that we have the different atomic levels, here's our nucleus, is because the electron behaving like a wave is a standing wave. So the fundamental is that first level, and then the different shapes of the waves, not doing a great job drawing this, but the different shapes of the waves were the different fundamental first harmonic, second harmonic, and those were our levels. And he came up with the idea of the matter wave. So these waves have a wavelength that's equal to Planck's constant divided by the momentum of the wave. So they have a wavelength and they have a momentum. That's why they're called matter waves. So lastly, we have a guy named Schrodinger who does an equation that says that the electrons in these wave patterns really only have a probability of being in this particular area. So the electron could be anywhere, but has the highest probability of being in this pattern right here. And this was the main idea of quantum physics. I did a better job of drawing this wave. And this model of saying that the electron is probably here, has the highest probability of here, is called the cloud model. And the name of that guy was Schrodinger. And that's kind of the end of the story. This is the current model that we have of the atom that is more precise than where we started, which was the idea of the Greeks saying that things are indivisible. Now, the story continues because it turns out that these particles, such as the proton and neutron, are not fundamental. They can be divided. So we have this idea of fundamental particles. Sometimes they're called elementary particles. And this is the idea that the particle cannot be subdivided. In other words, it can't be broken up into smaller parts. And remember the word atom, atomos, in Greek means cannot be divided, can't be chopped up into smaller things. So until the early 1900s, we had the idea of protons and neutrons forming the nucleus, and we had our electrons going around the outside. So this was kind of our crude model of the atom. And now we know, according to Schrodinger and de Broglie, that these are matter waves that have a probability of being here. And that was as far as we got. And we thought that the electron couldn't be chopped up, and that the proton couldn't be chopped up, and that the neutron couldn't be chopped up. In other words, these were fundamental particles. You can't get any smaller than them. Well, it turns out that there were some experiments done, actually a mathematical proposal, that the proton and neutron could be broken up into smaller fundamental particles, and that the electron already was a fundamental particle. So we have an elementary fundamental particle, and then we have these which are made up of smaller things. And these smaller things are called quarks. And the subdivision of this is called hadrons. So we have a whole classification of hadrons, which are broken up into our different quarks. And I'll explain the different names of the different quarks. There are a total of 6. But the way that they're combined give us our fundamental particles called protons and neutrons. And there's others, I'll show you. So here's our classification of matter, matter being stuff. So all stuff is made up of 2 different classifications called hadrons and leptons. We're going to focus on hadrons first. So hadrons are made up of quarks, and there are 6 different quarks. There are the up, down, charm, strange, top, and bottom. And the symbols for these just make sense, U, D, C, S, T, and B. And this E is elementary charges. So these are fractional charges. This is 2/3 of an elementary charge. So that's 2/3 of 1.6 times 10 to the minus 19th. Now, because we have matter, we also have antimatter. So we have the opposite version of this, that they don't give you a chart for it, but all it is the opposite charge. So an up quark is plus 2/3, and the way we do antimatter is we put a little bar over the top, and we just negative pick the opposite sign, so that would be minus 2/3. So if we go back to this chart, and we say we have hadrons, those are broken up into baryons and mesons. These are made up of quarks. So if it's a baryon, it's made up of 3 quarks. If it's a meson, it's made up of a quark and an antiquark. So it's the combination that gives us our new subatomic particle. So let's look at some examples. The most important one is the proton. And the proton is made up of an up-down quark combination. Well, let's look at what these are charged. Plus 2/3 and minus 1/3. So that's going to be plus 2/3, minus 1/3. And what does that add up to? That adds up to positive 3/3, which is equal to 1 elementary charge, and that's plus. And that's what we know a proton is. Well, what would an antiproton be? Well, an antiproton is made up of 3 quarks. It is a baryon, but it's made up of antiquarks. So that would be anti-up, anti-up, anti-down. So that would be minus 2/3, plus 1/3. We're just reversing the charges. And that's going to be minus 3/3, or a charge of minus 1 elementary charges. So what's a neutron then? A neutron is also a baryon, which means it's made up of 3 quarks. And what 3 quarks are they made up of? It's an up, down, down. So in that case, we have plus 2/3, minus 1/3, minus 1/3, which adds up to 0 elementary charges. And that makes sense because neutrons are neutral. They have no charge. So there are tons of other examples of these, and a few of them, you don't have to know all of these. You just have to know how to add the quarks and to recognize when it's a baryon or a meson. There's a particle called the lambda, and that is made up of an up-down strange. Because it's 3 quarks, it's a baryon. There's the sigma, which is made up of up-up strange. There is the chi particle, which is made up of an up strange strange, and there's something called the omega particle, which is a strange strange strange. So I'm just showing this to you because there are thousands of combinations of particles, but the main idea is if it's 3 quarks, then it's made up, and it's made up of 3 quarks, so therefore it's a baryon. If we put antiparticles through here, then that would be an antiparticle of that. But we didn't talk about the mesons yet. What are mesons? Mesons are made up of a quark and an antiquark. So some mesons, there is one called the pion, and the pion is made up of an up anti-down, one quark and an antiquark, or the kaon, and that's an anti-up down, and the eta particle is an anti-up strange. So a question that you might get might be, what is the classification of matter of the sigma particle? Well, if they give it to you, they're going to say it's up strange. You would say, okay, it's made up of 3 quarks, so therefore it's a baryon, and it must also be a hadron. So now we need to talk about the leptons. So the leptons are 6 fundamental particles, and they are the electron, the muon, and the tau. And these have increasing mass in this direction. The electron is -1, which makes sense, 1.6 times 10 to the minus 19th. If we have an anti-electron, it actually has its own name, it's called a positron. That would have the same mass as an electron, but have a charge of positive 1.6 times 10 to the minus 19. You can think of positron as a positive electron. And then we have our muon and our tau, each of them having a charge of -1. Each of these has a neutrino associated with it. Neutrinos are neutral. The word neutral is right in there, neutrinos. And they were originally thought to have no mass, but they have a mass that's so small that can be considered to be 0. And the only time these really come up is when we have nuclear decay. Sometimes a neutrino is ejected. So to show you an example of where a neutrino shows up, there's something called the weak force, and there is a weak interaction decay, which means that you could have a neutron and it could decay, in other words, break apart into other particles. So there's something called the mass number, which a neutron has an atomic mass of 1. It's approximate, it's actually tiny bit different than 1, but close enough to 1 that we just write 1, and it has a charge of 0. A neutron, when the weak force is involved, the neutron can decay into a proton and an electron, and a neutrino gets kicked off. So it's actually an antineutrino. Now, you don't need to memorize this, but what you do need to know is how these add up. So a proton has a mass of 1, an electron effectively has a mass of 0 in comparison to these. It's not quite 0, but it's very, very small. And then we have a charge of +1, and the electron has a charge of -1, and the neutrino has a mass of 0 and a charge of 0. So what do you need to know about an interaction decay? You don't need to memorize this, you just need to know that these all have to add up. So if we have a mass of 1 atomic mass units, 1 plus 0 plus 0, this adds up. Down here, when we look at the charge has to add up. The neutron is neutral, 0, and this is 1 and -1 and 0, so that adds up to 0. So what might they ask you? They might ask you, what is this charge, or what is the charge of a neutrino in this situation? And you can just look at the numbers and do the addition. That's really all that problem is asking you to do. Now, there are four fundamental forces, and we in physics really only are concerned with three of the four. But basically, you already know this one, which is anything with mass. What kind of force does that have? Well, that has gravitation, and we know that that is an attractive force. So if a particle has mass, then there's going to be a gravitational force of attraction. If it has charge, so anything with charge, well, what kind of force is that going to have? That's going to have an electrostatic force. And we know that electrostatic can attract, but it can also repel. And here's the new one. Quarks. This force only applies to quarks. Quarks have an additional force called the strong force. Now, it's called the strong force because it's the strongest force in the universe. But there's a catch. The strong force is only strong when the quarks are very, 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 very close together. As soon as the quarks start to separate a little bit, the strong force becomes weak. The strong force is an attractive force. And then the last force that I honestly don't really know much about because it's a much more complicated force, works on quarks and leptons. And you don't need to know this one, but I feel like for completeness, you should know what the four forces are. Even though it's called the weak force, it is still stronger than everything but the strong force. And this weak force is involved in decay. So when we looked at this, somehow these forces, this weak force, decay produces this situation. You don't need to worry about that though. So this is going to be a little bit confusing because this isn't something that you've ever learned about in chemistry or anywhere else in physics. And this is talking about this new force, the strong force. So the three characteristics that are important are that it only acts on quarks, it's attractive, and it's strong only at short distances. So as soon as we separate it a little bit, the force drops. So let's take two neutrons. So we know that neutrons are neutral, and because they're made up of quarks, there will be a strong force of attraction. So neutrons, when they're close together, will stick together. I mean, that seems weird because we think of neutrons as being neutral. Well, there's no electrostatic force, but there is the strong force. And there's a particle called the gluon that mediates this strong force. And you can think of it as the glue that holds them together. So what about a proton and a neutron? Well, a proton is positive and a neutron is neutral. So again, they're made of quarks, so there is a strong force attraction that holds them together. So this is the purpose of neutrons in a nucleus. As the nucleus starts to get larger and larger, the protons start to get further apart, and we need more neutrons to generate more strong force interaction, more glue, more gluons to hold the nucleus together. So here's the one that's most important, and that is a proton-proton. So the proton-proton, made up of quarks, so there's a strong force, so they're held together, but they're charged. They're both charged, so there's an electrostatic force. But when they're close together, the electrostatic force is weaker than the strong force. So the strong force at short distances is enough to keep two protons together. But if you push the protons far enough apart, the strong force becomes weak, and the electrostatic force is strong enough to repel them. So again, strong force, very strong when they're close together. Electrostatic force not strong enough to repel them, so they stick together. But if they're separated, then the electrostatic force becomes larger and the protons repel each other.
The objective of particle physics is to understand the basic structure and laws in nature, all the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm.
So historically we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead and so on, which are all made of different atoms. But a great simplification was made when we realized that all the atoms are just made out of three particles, the protons, the neutrons and the electrons. And just by adding more protons, more electrons, we get a different element, a different type of atom.
In principle, you can build a very simple universe with just protons, neutrons and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles.
So we were calling these new particles things like pi, sigma, delta and so on, and things got so bad we were running out of symbols to name these particles. So we started organizing these particles according to the properties they have. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles.
To simplify the picture, new fundamental particles called quarks were predicted. And the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the Standard Model. At the beginning, there were only 3 quarks. Then a 4th, 5th and 6th quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the Sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
The Standard Model is extremely successful, and it has predicted all the phenomena we have seen so far at the microscopic level.
This is a beautiful theory. It is self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle, and that's the Higgs boson. It's the holy grail of particle physics.
We know exactly what it should look like, and we have predicted this particle since over 40 years, and we use it in all our calculations and so on. We're pretty sure it's there, but we haven't found it so far. And now the LHC, which is already running, taking data, will find this particle if it exists. So this is the final piece of the Standard Model that we're looking for right now.
But there are still many unanswered questions beyond the Standard Model.
Some of the things that Atlas could discover that are beyond the Standard Model are things like dark matter, supersymmetry, or even extra dimensions.
All these open questions point to the existence of new particles which could be discovered and studied here at the Large Hadron Collider.